So quick recap, tolerance bounds, do a parametric approach, use your model fitted to data. If you do, great. If your model's wrong, that's a bummer because you could be inaccurate. And if you don't have enough data, you might not know you're inaccurate because you don't have enough information to tell whether your distribution is right or wrong. So what are some ways we can address this issue? Well, let's visit some currently available methods. And I'll start with a favorite one of people, which is use order statistics. You take your data, you sort it lowest to highest, and then you can use those sorted values as bounds because they have a nice property of being distribution free. The capital F there, that's cumulative distribution function of some distribution model. You'll notice in the final answer, it's not there anymore. So this works independent of any underlying distribution model. This is great. This is awesome. I wish I could end my talk here. Unfortunately, there's a catch. And that is, so you can control the percentile you're interested in. It's maybe given to you. You control your sample size, sure. But once you put those in, your confidence level gamma is determined. It may be what you want, it may be close to what you want, it may not be close to what you want. You don't have control over that outside of adjusting P or N, which of course can be either impossible or very difficult to change. So what are some things that we can do? Well, so this may not work. We don't have a lot of control over getting that confidence exactly where we want. Maybe let's extend it to more of a semi-parametric approach. What are some assumptions that we have to make now in doing this? Well, one approach that was proposed back in the 80s was this idea of, well, let's say I take my minimum order statistic and its coverage is too low. I want 95%, it's maybe 92. I do the second one, I have 98. Well, these folks said, maybe I can interpolate between the two and find something in the middle that's actually closer to the confidence level I want. So that's the idea of interpolated order statistics, and they kind of look like that. There are two kind of families of how you determine that weight. One, the simplest, is what these original guys looked at, and then it's been extended a bit. I'm going to refer to it as the Barron and Hall because they're the one who kind of generalized it. And it's simply, what is the confidence of the low? What's the confidence at the high? Use that simple interpolation technique to at your weight. The other one by these two folks, I'll call it the Hudson because again, he kind of generalized it, is use what's called a fractional order statistic. They were proposed back in the 70s. It's that idea of I have my lowest, my 1, my 2, maybe there's a 1.5 order statistic out there. There's some theory around that. I'm not going to go into much detail on that, but that's where that comes from. And they're both just trying to say, how do I determine that weight? Well, unfortunately, there's another catch with these. One, they're no longer distribution free. So these weights have generally been chosen to be conservative for a wide array of distribution models. And also, kind of obvious, it only works if the actual confidence you want is between the two order statistics. What if I'm below? What if I use my minimum and it gives me 98% confidence and I want 95? What do I do then? What if it isn't? Well, this brings us to the idea of extrapolation. If we can interpolate, maybe we can try and extrapolate. And so the easiest one is just, okay, I'll just do it in extrapolation, or maybe if I'm interested in the lower bound, maybe the two lowest order statistics. Well, a recent paper by one of our co-authors and a colleague of his showed that if you do that, your actual coverage could be much smaller than what you want. So we have that issue. In the 90s, Schultz tried to derive something where he said, maybe I'll take my order statistics and I'll plot them against their actual coverage. And that gives me a bit of a relationship. It might not be a linear one, so I'll try some sort of transformation. It's kind of similar to a Box-Cox-like transformation to linearize that relationship. And once I do that, then I can use that relationship to extrapolate down. So there's a bit of a tuning parameter, and he created a method to try and help tune that parameter to get you the confidence you want. Well, a recent paper did a comparison study between Schultz and Hudson, which is, if you use Hudson in this context, it's kind of similar to standard linear extrapolation. And they found that, again, it's no longer distribution free. It's very sensitive to the underlying distribution model. And furthermore, they had no clear recommendation of which one was better. So at this point so far, I've told you, here's a bunch of options. They don't seem to be working out. There is hope, don't worry. We're going to revisit the interpolated intervals real quick. So one of the things there is you're trying to find the value that gets you as close to your desired confidence as you want. It may not get there exactly. So some folks said, well, maybe what I can do is adjust my target level that I want purposely go off target so that it calibrates the actual value I want. So that's this idea of calibration. And it's been done for both classes of intervals. And again, it's just this idea of what they'll do is they'll assume a normal distribution under the hood and then say, you know, here's the actual level you need to target if you want, say, 95%. Maybe it's something closer to 90% you target to get the actual coverage. To the best of our knowledge, no one has considered this for extrapolation. So we said, okay, we'll give that a try. Maybe this could help answer our questions. So what do we calibrate? Well, of course, the first obvious answer is we'll do like these guys did. We'll calibrate the target confidence to achieve our accuracy. And you can do that. But if you do, what you're going to find is that the values you need to target fall outside 0, 1. You get nonsense targets. So that clearly isn't going to work. So then we said, maybe instead of the confidence level, what is the actual weight value I need to achieve this level? So in this case, sort of calibrate, maybe that's not the right term, but essentially determine what is the actual weight value I need to get this. So our goal is to determine the appropriate weight to achieve the actual confidence at or above. We still are going to acknowledge that we might need to be a little conservative. And we're focusing on positive data. So what we're actually going to do is sort of a log linear extrapolation, where we take the log transform of our data, compute the extrapolation, and then convert back. We're going to assess our coverage on the original scale after we transform back, but the weight is going to be on the log transform data. So we started off with a bit of a pilot study. Specifically, we focused on what would we think the calibrated weight is going to be a function of several inputs. Obviously, it's going to be a function of the underlying model. That includes its parameters, what our target confidence level is, the quantile we're interested in, and the sample size. So we set up some factors. So here's our factors. We had 4 distribution models, 2 common target confidence levels, and a couple of quantiles and shape and scale parameters, just to get a sense of what's going to impact what. So when we did that, we did a full factorial design and all of that. This is a simulation study. And we determined the correct weight the following way. For each run, so each combination of those factors, we ran 10,000 simulated experiments, and we started with initial guess for the weight. Then we computed the coverage based on those simulations. And then if it was within 0.001 of our coverage, we said we got it. We're going to record our correct weight. If not, we try again until we get within that area. So our weight is our response. After that, we found 2 key things from our study. First off, of the 4 models we considered the most extreme, we want to look at more extreme weights. So our weights are going to be less than 1, less than 0, because we're extrapolating down. In this case, we're focused on the lower bound. I didn't mention that before. So we want things that are going to be a little more extreme, because that means they're going to be a little more conservative. The gamma and Weibel models did that for us. So we said, okay, we might want to use that to help determine our model, our function. And of the distribution parameters, the shape parameters seem to have a meaningful impact. The scale parameter almost did nothing, which kind of makes sense. The scale parameter is more a location. The scale will actually determine the behavior at details that we're interested in. So with that in mind, we said, okay, let's conduct our formal simulation experiment. So here's the official experiment we ran under these factor settings. So we reduced our distribution models. We updated the number of quantiles, sample size, and the shape parameters we looked at. We didn't look at a value of 1. That's an exponential. That's too extreme. We wanted to keep this first. And we tried to pick a range of feasible quantiles that where we could go a little extreme and not extreme, just to get a sense of range. Each run was done the same way as it was in the pilot study. And I ran it in R and analyzed it in Jump. Just a quick note to show that we used all kinds of software to do this. Here's our results. I just connected points here, but that's pretty amazing. Those are lines. Now we have transformed the responses, and we did this prior to plotting anything. So the quantile and percentile, we did a logic transform, the shape and the sample size, get a log transform, and that's to put everything on the same scale. But just looking at these, you can already tell what's affecting what. So the target confidence, you can see that effect in the different scales. There's clearly a response with the quantile. There's a really strong response. There's even a tiny bit with the slope, where you can see that for a very small slope, once we go from that to 15, that's a big jump. But if we go 15 to 20, it's not as big. So there's definitely a diminishing return with the sample size, which kind of makes sense. At some point, you increase your sample size large enough, you no longer need to extrapolate. So we've got this visualization of relationship. This clearly indicates that we should fit some sort of linear model. So that's what I did. Don't worry too much about all the details there. Basically, I threw everything at it but the kitchen sink. So this is me after removing everything that wasn't significant. We can see our top three are the quantile and target confidence. They're overwhelmingly top. Right beneath that is the distribution. That makes sense. We know that's going to have an effect. The shape parameters in there somewhere. There's a bunch of interactions, complex interactions going on here. Our actual by predicted, we're doing okay. 0.998 R squared, not too bad, you know. But this isn't our final model because there are things in here that we obviously don't know going in. Specifically, we want to model that's robust across distribution models. So we need to get rid of some things, but we need to do it in a systematic manner. Based on this profiler plot of the effects, we notice that the Weibull is slightly more conservative than the gamma. Okay, so maybe we can use the parameter estimates for that model in our final model. That's a way to get rid of the distribution effect. For the shape parameter, there's a bit of, it's not a very strong effect. And an easy way to do it is I'm using the log. Well, I'll fix the shape parameter at 1. That essentially zeroes out the shape parameter from our model. And by doing all of that, what we've implicitly done is assumed an exponential distribution for our model because we have a Weibull with a shape parameter of 1, which is interesting because that's what Schultz did in his paper. He actually had an implicit assumption of an exponential model. So that was good to confirm. We're at least tracking with some previous results. So doing that, this top part shows you what happens when we remove the shape parameter. We're already starting to get some spread in the lower end. These are the more extreme quantiles. If I were to actually take the values of the true distribution for Weibull, that spread would get even wider. So I'm performing very bad statistics by actually reversing what you would probably want to do. I went from perfectly straight to now I've got some spread, but we're doing it. We know what's going on there. We know exactly what's causing the spread. This is our final model that we get at the bottom for the weight. And again, more discrepancy at extremes. That makes sense. The farther out you go, the more unstable we're going to be. Just a quick note here on the model. It's interesting to note that the coefficients on the target confidence and percentile, they're similar in opposite sign, which might hint at some sort of log odds ratio behavior going on. We'll go back to that later. Just wanted to point it out real quick. All right, now let's actually assess how well we're doing. So we followed this up with a confirmation experiment where we added situations that the model had not seen. So we added 2 more distribution models that clearly hadn't seen. We kind of filled in the gaps with the quantiles, added a few more sample sizes. We even threw back in the scale parameters just in case to see how sensitive it was there. We also threw in the shape parameter of 1 because we knew that was going to be extreme case. While also confirming and seeing how well it performs in these new situations, we also said we're going to compare it to other methods. So we've got a standard log linear extrapolation using the Barron-Hall. That's the simpler approach. We also compared it to 2 parametric methods, the log normal and Weibull distribution models, because those are the popular parametric approaches. And that was done using the TOGS package in R. Here's our plot. Let me break it down for you. There's a lot going on. Top row, that is our method. And we're pretty close. There's a horizontal line at about 0.9. You can't really see it because our points are around there, except for n equals 20. We really aren't doing well. And the reason probably is for this confidence, 20 is the threshold of extrapolation and interpolation. In fact, you might want to just interpolate. We did it for 95% confidence. That's no longer the case. They're all pretty nice and tight. Log normal, it does really well if the data is log normal. Otherwise, it is a really poor choice. That is what we would expect with the parametric method. It is not very robust. Standard extrapolation, that's the behavior you kind of see. We're really conservative, very far off, but as we get closer, we become really anti-conservative. We're not consistent. Our closest competitor is actually the Weibull, which actually performs pretty well, even in cases where it's not Weibull. So what I'm going to do is focus on those 2 next. So if we get a more detailed look at what's going on, we'll notice that there are places where we're pretty conservative. We might get a little more conservative as things change. The scale parameter is not on here because we actually found it actually didn't have an effect. That was good to know. But one interesting thing to point out here, so compared to everything that's not Weibull, we're actually less conservative than the Weibull. That's good. But in the case where it is reliable, something weird has happened. We appear to have beat the parametric method at its own game, which was very surprising. What might be going on here is it's more, for the reliable, it's more of a numeric procedure to get the bounds. So that's probably why it's not doing as well, because it should be actually more on top of the line. But apparently we beat a parametric method at its own game. So that was very surprising. I'll briefly run through this real quick. This is more of a practical interpretation. You know, we get these nice bounds, but of course I can have accurate coverage and have a bound that's practically zero. So it's not very informative. So this is a way of a sanity check to say, you know, are we actually getting reasonable bounds? For 90%, sure, we're getting some reasonable bounds. For 95% confidence, especially with very low sample sizes, we are starting to get into areas where I'm giving you zero, unless you are dealing on that small scale. So that's something just to keep in mind. We do, as you increase the sample size, get something more reasonable. So in summary, we were pretty successful. Our method did succeed at better calibration of the target coverage. We're more robust to model misspecification. And there was that one case where we apparently beat a parametric model, but I'm not going to brag about that too much. So we do outperform the standard log linear extrapolation, but this isn't the final answer. This is the first step. This is a very empirical approach. We found something, and we found some interesting behavior that's worth exploring further. Obviously, we would prefer something that's a little more grounded in theory to actually investigate this behavior. So the model itself is already hinting at that type of behavior. And that's all I have. Thank you very much.
Give Caleb another minute or two for questions since the session chair delayed his talk. So any questions for Caleb? While I pull up Greg's slides. Do you want to?
Have you done examples where you have confidence bound or confidence levels much closer to 100%? Does it break down at all as you get to those cases?
I think there was some initial exploration at the beginning where we looked at 99%, but once we got into it, we really stuck with 90-95% just because it was common. But it would be interesting to see, I think, with 99% to see how it starts to break down, if at all. Yeah.
If you're pushing for anything beyond 99%, you're probably trying to gather enough data anyway that you don't need to use.
Right. What might happen with those is if your sample size is small enough, you could already see with the 95% where I could give you accurate coverage, but the Thomas bound is, I'm basically saying use zero. So it becomes a nonsense bound, or at least nothing practically useful. So.
Any other questions? Let's thank Caleb again.